Hello students, today topic is damped harmonic electric oscillator. An electric oscillator is simply a combination of inductors and capacitances placed in parallel. An AC current is induced in the circuit by mutual induction, and this current stores in these two components in the form of magnetic field and electric field and keeps on changing for certain time and produce electrical oscillations. But due to the presence of resistance of these connecting wires and components, some current loss is always there, and this loss of current decreases the amplitude of oscillations produced, and this loss of amplitude in the oscillations may be shown by this diagram, in which you see the charge stored or charge in the circuit due to the electric current and variation with time, that is shown here, and the total charge is decreasing with time, and such oscillations are called damped oscillations. And the electrical oscillator which produce this kind of oscillations is called damped harmonic electric oscillator. So that is the basic idea about the harmonic electric oscillator with damping factor. Now in this circuit you just see there is no source of electric current. Whatever current is there, that is induced from the external circuit through mutual induction, and according to Kirchhoff's law, the sum of all the voltages dropped across different components L, C and resistance, that must be equal to 0, and the potential or induced EMF on inductance, that is given by EL, that is L di by dt. I is the current induced through external circuit. EC is the EMF across capacitance. Q is the charge stored on the plates of capacitor through this current. And here VR or EMF on resistance, that is given by I into R. I is current, R is the total resultant resistance of the circuit. Now applying Kirchhoff's law, we can write the sum of all the potentials like this: EL plus EC plus ER equal to 0. Here it is 0 because there is no source of EMF in the circuit. Okay, so let us put the values of EL, EC and ER from these terms. We get this equation: EL is this, L di by dt plus Q by C plus IR equal to 0. Now here current I in terms of charge, we can write that is rate of flow of charge, that is called current, and this term di by dt, that can be written here as di by dt is equal to d by dt of I is here, that is dq by dt, so it gives you d2q by dt square, double differentiation of charge. And if we put all these values in this equation, we get L d2q by dt square plus value of resistance dq by dt R, this is Ri, plus Q by C equal to 0. Here we can just divide whole equation by this value of L, inductor. We get d2q by dt square, L got cancelled. Here R divided by L dq by dt and Q L over C equal to 0. Now R over L and Q 1 over LC can be placed for different values. We substitute omega naught square equal to 1 over LC. This 1 over LC is placed, omega naught square, and we consider these are the oscillation. Omega naught square is the frequency of oscillations of undamped oscillator, where that means in an oscillator where though no damping is there, or free oscillations. And R over L, this factor is placed as 2B. B is here constant, which represent the damping, because R resistance is responsible for the loss of current in the circuit. Therefore, B represents the damping in the circuit. And the result comes out to be in this equation, that is d2q by dt square plus 2b into dq by dt plus omega naught square q equal to 0. We take this equation as 1, and this equation is called differential equation of damped harmonic electric oscillator. This is linear equation, and any combination of different solutions of this equation may be there, and sum of all those solutions will also be solution of this equation. So that is due to the property of linearity of the solutions. And we assume, because it is a linear differential equation, we expect that its solution will be kind of this: q is equal to c e alpha t, where c and alpha are constants, and the value of these we can find later on. If we substitute this solution, because solution is a mathematical expression which satisfy such equation, and if it has to satisfy this equation, we can substitute the value in this equation, and let us see what result we get. So to put this value here, we need what differentiation of q here and double differentiation of q here. And to find these values, let us find firstly dq by dt, which gives me alpha c e alpha t, because this alpha will come down here. d2q by dt square will give you one more alpha here, alpha square c e alpha t. Now substituting all these values in this equation, what we get is here double differentiation, this term, that is alpha square c e alpha t, plus here dq by dt, this dq by dt, so 2b into alpha c e alpha t from here, plus omega naught square, and the value of q which we have assumed here, that comes out to be like this. It is not q, this is c e alpha t, equal to 0. Now in all these terms, you see c e alpha t is common, c e alpha t, we take this term common here, c e alpha t, and we left with alpha square here plus 2b alpha here plus omega naught square here, that is equal to 0. Now here we have two factors, c e alpha t and one bracket, and the result of these two factors, product of these two factors, comes out to be 0. And result is only 0 if one of these two factors is 0. But c e alpha t we have assumed it cannot be 0. Therefore, to get the result 0, this bracket should be equal to 0. And so, since c e alpha t cannot be 0, therefore this bracket should be equal to 0. But this equation here, it is quadratic equation in terms of alpha, alpha square 2b alpha plus omega naught square, where omega naught square you can compare it with the a x square plus bx plus c. So by using quadratic equation property, we can find the solutions of this equation, because this quadratic equation will be having two solutions. So we find these solutions as alpha is equal to minus 2b plus minus, because here we have 2b, so minus 2b, 4b square of b, that is b square minus 4ac. So b is here 2b, so we get 4b square plus minus 4a, a is 1, so omega naught square c square root. Now in both the terms we have 4 can be taken out from the square root, we will get 2 here, and another 2 is here in the numerator. Both terms have 2, and in the denominator we have 2, so these two will cancel. and we will get a result minus b plus minus b square minus omega naught square, and alpha now come out to be minus b plus minus b square minus omega naught square under root. Here we have now term q is equal to, because this alpha we have to put in this equation, so let us substitute this alpha here, multiply with the t, so we get equation of this kind. Q is equal to CE, that is value of alpha into t. This is now solution of the differential equation. We have this equation number 1. This is linear differential equation of the damped oscillator, electrical damped oscillator, and this is the solution. That means the variation of charge in the circuit will be shown by this equation. Now this equation will be a combination of various results, because there is a term under square root, that is b square minus omega naught square, and due to this negative sign we can have 3 different values. How? That one value may be there where b square will be greater than omega naught square, and such value in which b square is greater than this, because b, it is damping factor, and damping mean a value of resistance, and if value of resistance is high, then such oscillator, the oscillations of this oscillator will be known as heavily damped, and the oscillator is called heavily damped oscillator. The reason is because B is damping factor, or damping properties hidden here. And second case is B square is equal to omega naught square. Second case may be there. So such case is called critically damping or critically damped oscillator. Third case may be when B square, that is damping, is very small, and when damping is very small, then it is called lightly damped. So there may be 3 types of dampings depending upon the values of B and omega naught. And now we will discuss all these 3 types of dampings. Let us take the first case of this solution in which b square is greater than omega naught square, like this. And in this case, this factor will be positive. That means square root term will be positive. And we can rewrite this equation as e minus b into t, that we take common. And I told you that this is because this is a solution of linear differential equation, and the sum of all the partial solutions will be the sum of all the partial solutions will also be the solution of that equation. So therefore we take first part, that is with the plus sign, and another with the minus sign. We can divide this, we can write 2 factors, that is C1 e b square minus omega naught square delta t square root, plus C2 e minus b square minus omega naught square root t. But we know that Ex is written as cos hyperbolic x plus sine hyperbolic x, and E minus x is written as cos hyperbolic x minus sine hyperbolic x. And here, because E minus x, and we can take it as factor as x, so we can write this equation again. Q is equal to E minus bt C1 from here, C1, and we expand this factor, that is cos hyperbolic b square minus omega naught square root t plus sine hyperbolic b square minus omega naught square root t, plus then we write C2 second term, that is we expand this part C2, and this cos hyperbolic b square minus omega naught square root into t, minus sign now. sine hyperbolic b square minus omega naught square hyperbolic t. So we have expanded this and this exponential terms in terms of sine and cosine terms. And you see this is solution containing cos hyperbolic and sine hyperbolic. And both these functions are not oscillatory functions. These are non-oscillatory functions. Okay. And now we can simplify further this equation by collecting cos terms and sine hyperbolic terms. So if we combine cos hyperbolic term from here to here, then we get cos hyperbolic b square minus omega naught square square root t. This is common, and remaining factors from here c1 and plus c2 we write here. Plus similarly, you collect sine hyperbolic terms, that we write sine hyperbolic b square minus omega naught square square root t, and the factors we get here c1 from here, but minus sign here, that gives you c2 minus. So we get c1 minus c2, and for simplification we can put c1 plus c2 as a and c1 minus c2 as b. So the equation comes out to be like this, that is a cos hyperbolic b square minus omega naught square half t plus b sine hyperbolic b square minus omega naught square, this is half means square root into t. Okay. Now this solution containing cos and hyperbolic functions which are non-oscillatory, and therefore it gives you non-oscillatory vibrations of the charge, this charge. That means between inductor and capacitor charge, current is exchanging, but it is not oscillatory. It will decay with some factor because it is not oscillatory. But the question is, if it is not oscillatory, what kind of variation is this? For that we know that the hyperbolic functions have this kind of variations. Cosine hyperbolic function is of this nature and sine hyperbolic function is of this nature. Now we want to know how these two functions are affecting the variation of charge. For that we consider the initial condition when there was no current source in the circuit at time t equal to 0. What was the value of this equation? So we can write when t was 0 in the starting and there was no current, and when no current no charge was there, then the value of this equation comes out to be this q is 0, e minus b 0, a cos hyperbolic b square minus omega naught square square root time is 0 plus b sine hyperbolic b square minus omega naught square square root time is 0. So this 0 multiplied by this factor makes it 0. E0 is 1. This side we have 0. But a cos, if you multiply with this cosine factor, you will get cosine 0 is 1. But sine 0 is 0. Sine hyperbolic is 0. So therefore, what we get is this factor is 0. We get a only, and this side is 0. Therefore, a is equal to 0. So what we get is the coefficient multiplied with the cosine hyperbolic function, that vanishes. A is 0. It means there is no role of cosine hyperbolic function in the variation of this charge. So at any time, what will be the effect of this hyperbolic function, that we can write here that a is 0, then the value of this solution will be q is equal to a is vanishing here, therefore we don't write it. So we get e minus bt multiplied by b sine hyperbolic b square minus omega naught square square root into t. Okay, so it means now only sine variation is there, and sine variation from 0 onwards is like this. It means that in the starting, when time is small in the starting, then the exponential function will be very small and sine hyperbolic function will dominate, and therefore the variation will be given by sine hyperbolic function from here to here like this. Therefore in the starting, the given impulse, the variation will be like this as the sine function going this way. But at certain point where these values will equalize, this point will reach, and after that exponential function will dominate, and therefore the charge will decrease exponentially with this factor. Okay, so the solution will come out to be like this in the non-oscillatory heavily damped oscillator condition, and the variation of the charge will be given by this, that this is the maximum value, that is amplitude, and after that it will decrease this way. And in this case it takes long time to come to initial value of charge, that is 0. Now second case is when this is first type of damping here is that is finished. Now second kind of damping is, that is critical damping, when b square is equal to omega naught square. That means when damping effect is almost equal to natural frequencies of square of the natural frequencies of the undamped oscillator. In that case, this solution b square minus omega naught square will become 0, and we will get only Ce minus Bt. But Ce minus Bt will not satisfy the differential equation, because the differential equation of damped oscillator have two terms. One term is with the charge, another term is with the current. So if you put charge equal to 0 or charge variation, there is no term which is showing the current variation, and for that we need solution of this kind in which A will have the units of charge, and B will have the unit of current. So therefore charge and current values should be there in the solution. Okay, for that our assumption b square is equal to omega naught square is not correct. What we take is that b square and omega naught square are almost equal, not exactly equal, and when they are almost equal, in that case the difference will be having some infinitesimal small value. Some difference will be there, but difference is very small. And when this difference is very small, then we can write this equation here, b square minus omega naught square square root will be replaced by delta. And if it is so, we can rewrite this equation as q is equal to c e minus, this is b plus minus delta from here multiply by t. And we can rewrite it as in by taking plus and minus two terms separate. So e minus bt is common here. Inside C1 E plus delta t plus C2 E minus delta t. Because delta is very small, therefore we can expand this delta in terms of series, and therefore C1 is equal into 1 plus delta t plus so on, because higher terms can be neglected as delta is very small and the powers of delta will further be very small, plus C2 1 minus delta t and so on. So if we combine these terms now, C1 from here, C2 here, we get this plus delta terms, we get C1 minus here sine delta, C2 delta t. Now let us substitute this C1 minus C2 into delta equal to B, and C1 plus C2 equal to A. By putting these values, we get q is equal to E minus Bt. In bracket we get here A plus B into delta into T. So A plus Bt. So ultimately we get the solution as it was required here. So this kind of solution we get here, which shows it will satisfy, this equation, this solution will satisfy the differential equation we have derived earlier for the damped oscillator. The variation of the charge, this charge with the A plus Bt term, it comes out to be in as shown in this diagram. Here in this case we have T this side and charge this side, and the value of maximum value of the charge, that is we can take amplitude as, and it decreases sharply with the exponential term, and it decays rapidly to zero. That means the value of charge will comes to zero very sharply in small time. And but you see this this variation is also non-oscillatory, it is exponential decay. It is so in first two cases, first two type of dampings, heavily damping, heavily damped oscillator and critically damped oscillator, both the cases are non-oscillatory. And we have seen that in case of heavily damped oscillator, it takes long time to come to zero, whereas in critically damped it takes smaller time to reduce to zero. Now third case of damping is when b square is less than omega naught square, and since damping part is hidden in b square, so this damping is less or small. So such case is called lightly damped oscillator. So in case of lightly damped oscillations, we can have b square minus omega naught square will be equal to or less than 0, because b square term is less than omega naught square. So that means it is giving you a negative term. So anything negative in the under the square root, we can write it as negative sign out omega naught square minus b square this way, and this negative inside the square root will give you minus 1 square root, which is iota. We take it as iota, and in terms of iota we can write the solution as Ce minus Bt E plus minus iota omega naught square minus b square t. Here this omega naught square minus b square can be substituted as omega square. Here omega naught square is the natural frequency of oscillations which are free from damping, whereas this omega square is the frequency of oscillator which is damped. So it shows that the frequency of damped oscillator is less, because less than the undamped oscillator frequency, because something is being reduced, and this reduction is nothing but due to the damping factor. And this damping of the system will be due to the resistance present in the circuit for the current. Now if this solution we write here, this one Ce minus Bt E plus minus iota omega t, we put this value here omega, and since iota term is there, so we can write that E iota theta, we know the properties. E iota theta can be written as cos theta plus iota sin theta, and E minus iota theta is equal to cos theta minus iota sin theta. If we put these values here and then C2 multiply by cos omega t minus iota sin omega t, these are the terms we get by using these two terms here. Then next we get E minus Bt, inside we collect cos terms, cos omega t, from here C1, from here C2, plus iota sin omega t we take common, and C1 we get from here and minus C2 we get from here. And then we can just substitute C1 plus C2 as A1 cos phi, and iota times C1 minus C2 we put A1 sin phi. We can take A1 common here, so we can write cos omega t cos phi plus A1 sine omega t sine phi. A1 is amplitude of the damped or lightly damped oscillator that we can take out here. Inside we left with cos omega t cos phi plus sine omega t sine phi. And in trigonometry formula, you know, this is cos omega t cos phi plus sine omega t sine phi may be written as cos omega t minus phi. And outside this bracket we have a1 e minus bt. So it shows that the oscillations are now varying with the cosine function, which is a harmonic function, oscillatory function. But the difference is that amplitude is not constant now. Amplitude a1 is not constant because it is multiplied with the exponential factor, which is negative and decaying. That means it is a decaying factor. So it shows that the total amplitude will decrease with time, though the oscillations are there with the cosine function. And this thing can be shown in diagram like this, that the variation is with the cosine function, but the amplitude is not constant. Amplitude is decaying, like decay can be shown by this, that is exponential decay, but the oscillations are there and varying with cosine function. So the resultant oscillations of lightly damped electrical oscillator in which charge decreases with this way with the passage of time. So we have discussed all the three types of damping, and these three type of damping can be shown in a same diagram like this. If we take time along x-axis and variation of charge along y-axis, and let us assume amplitude a, that is maximum value of q in the circuit, then first case we have seen that due to sine hyperbolic function, the variation of charge will be there and it will come to the value 0, but after very long time. Whereas in second case, when critical damping is there, the amplitude or charge, total charge, will come to 0 in very short time. So because it is coming very sharply to original position of charge, original value of charge, so it is called critically damped. It is called heavily damped. Critically damped is also known as deadbeat system. But in third case, when the damping is very small, in that case the amplitude will decrease, but variation is oscillatory, and oscillations in our case is varying with the cosine function. So all these three cases you can show. One is heavily damped case, then second, when it is comes to 0 very sharply, that is critically damped, and third case is when it is varying with the cosine function, or it is oscillatory with the decaying factor, decaying amplitude, that is called lightly damped case, lightly damped harmonic oscillator. So these are the three types of damping in electrical damped harmonic oscillator. That's all.